In today's video, we are going to study limit state of collapse and stress block parameters. First, let us see the assumptions in the limit state of collapse. So this already they have given in IS 456 2000, clause number 38.1 and page number 69. First assumption is that plane section normal to the axis remain plane after bending. So that means the strain profile what we are going to get, it will be like a straight line. It is going to vary linearly. That means strain at any point on the cross section is directly proportional to its distance from the neutral axis. That means it is going to vary linearly across the cross section. Second assumption is that the maximum strain in concrete at outermost compression fiber is taken as 0.0035 in bending. So this is our neutral axis. Above this we have compression, below we have tension. This is the outermost compression fiber. So here at this point the compression fiber, it is maximum strain is limited to 0.0035. 0.0035. This is the maximum strain in the concrete. If you see this stress strain curve also, this is stress and this is the strain, what we have strain we have. If you see the stress strain curve, so if you see along the strain, the maximum strain which it is being taken is 0.0035. Therefore the maximum strain taken in the concrete will be 0.0035. Then next is this third assumption is that if you see this stress strain curve of this concrete, it is going to be parabolic from 0 to 0.2. If you see the strain profile, so from 0 to 0.2 it is parabolic, and stress also from 0 to FCK. So this is strain is 0 to FCK, it is parabolic from here up to this point. The next is stress from 0 to FCK. 0 to FCK, it is parabolic. After this, what happens that stress, it will remain constant. If you see, this is the stress parameter stress we have. So stress, it will remain same. That is FCK will have. From 0 to FCK, it is parabolic. The next after that, it will remain same. But whereas in the strain, if you see, from 0 to 0.002, this strain profile is parabolic. After that, strain will be like it will be straight up to 0.0035. So that is what it says. So this is the characteristic strength of concrete FCK we have. So as to get the design strength, what we do, so this is FCK. So this will be reduced by 33% because this is tested in lab and all, shape factor and all we have. So that is being reduced to 33%. So therefore FCK, it will be like 0.67 FCK. 0.67 FCK. This will be 0.67 FCK of the curve. Then next is that again to this, so as to get the design flexural strength of the concrete. So what we do is that we apply a partial safety factor, 0.67 FCK we have divided by 1.5 or gamma m divided by 1.5. So as to get the design flexural strength of the concrete, that is 0.67 FCK divided by gamma m. So partial safety factor for concrete is 1.5. So if you divide, if you simplify, you will get answer as 0.446 FCK. So this will be the design flexural strength of the. Next is the stress strain relationship in concrete could be either rectangular, parabolic or combination of both rectangular and parabolic curves, which should be agreeable with the experimental results. So you can have rectangular or parabolic or combination of both. Thing is that it has to get agreeable experimental results. Then next is the stresses in the steel bars used for reinforcement are derived from the representative stress strain curve for the type of steel used. Then next is the perfect bond exists between the reinforced steel and adjoining concrete. There should be perfect bond between the steel and concrete. Next is tensile strength of concrete is neglected. So only if you see the stress strain curve further, if you see here, so below this also like concrete, it is going to take certain tension, but what happens that we are going to neglect, we assume that concrete is not going to take any tension. Then next is maximum strain in the tensile reinforcement in the section at failure shall not be less than 0.87 f of phi divided by es plus 0.002. That means if you see this is the strain profile. So concrete already we have seen it is limited to 0.0035. Similarly, the maximum strain in steel. So top is compression, bottom is tension. So this in the tension reinforcement, the maximum strain should not be less than 0.87 f of phi divided by es plus 0.002. All these things they have given in the code book. So let me show you in limit state of collapse flexure. In assumptions, they have given all the assumptions. Plane section normal to the axis will remain plane. Plane section normal to the axis will remain plane after bending. What all things I have covered, what all curves I have shown, it is being given in the code book. Maximum strain is 0.0035. Then next the relationship has to be like a rectangular, parabolic combination of both the things and all. The next is the tensile strength of concrete, it is ignored. The stresses in the reinforcement are derived from representative stress strain curve. So if you see here, they have given the representative stress strain curve. Representative stress strain curve for cold work deformed bars, or you can refer this mild steel, the steel bars with the yield, definite yield point. So these are the representative stress strain curve for the reinforcement. Then next is that the maximum strain in the tension reinforcement shall not be less than this. Already this also I have shown. So everything it is being given in the code book. If it is being asked, you can write. So everything it is being given in the code book. If it is being asked, you can write it directly. Next, we'll go to the stress block parameters. We'll consider one singly reinforced rectangular beam of width b and effective depth d. Effective depth is nothing but distance from the extreme top compression fiber to the center of this tensile reinforcement, centroid of this tensile reinforcement. That is nothing but the effective depth. Next is neutral axis. This is the neutral axis we have. Above this we'll have compression zone. This is compression zone and this is the tension zone we have. Then next is only will provide reinforcement in the tension zone, that is AST, that is area of steel. Then next is XU. XU is nothing but depth of the neutral axis from extreme fiber, distance from this point till this point. This distance we call it as the depth of neutral axis, which is denoted by XU. This is the section showing the details. The next is this is the strain diagram. So at the neutral axis strain will be 0. So linearly it is going to vary. At the top it will be, at the top and at the bottom it will be maximum. So therefore maximum strain in the concrete, it is limited to 0.0035. This is as per the assumption what I have shown. Then next is this in the steel, that is epsilon s. Epsilon s, that is equal to 0.87 f of phi divided by es plus 0.002. So it should not be less than this values. This is steel, concrete, and bottom one is the steel, strain in the steel. Then next is this is the stress diagram. So what happens is that above the neutral axis we have compression. So therefore up to a strain of 0.002, that means up to this point, for example, strain we have 002. Up to the strain of 0.002, that curve will be, this curve will be parabolic. After that it will be straight. After that it will be straight. Up to 0.002, up to this point it is parabolic, 0.002. After that it will remain same up to a strain of 0.0035. Then next is the stress in the steel. It is being given by area multiplied by the yield stress. So f of AST into f of y we have. So we will multiply safety factor, f of y divided by 1.15. So factor of safety used for steel is 1.15, that is 1 divided by 1.15, it will be 0.87. So therefore this will be 0.87 f of y into AST. So let us calculate now. We'll take first this strain diagram. This is the strain diagram we have, strain in the concrete and strain in the steel. So this is nothing but XU. So what we'll do, up to strain stress is parabolic up to a strain of 0.002, that is up to this much. So we'll take this distance as x1. So above that we'll take it as x2. Total depth is nothing but XU, that is depth of the neutral axis. So let us try to calculate these parameters, that is x1, x2. So how to calculate? We can consider this as a similar triangles and we can calculate, that is x1 divided by xu, that is x1 divided by xu, that is equal to this strain, that is 0.002 divided by 0.0035. So if you cross multiply, if you take this xu this side, so if you take this xu this side, so x1 will be equal to 0.002 divided by 0.0035 multiplied by xu. So further if you simplify, it will be 4 divided by 7 of xu, that is nothing but value of x1. Next is we'll try to calculate this x2. So this x2 will be nothing but total depth is xu minus x1, if you subtract, remaining will be x2, that is xu minus of x1. xu we have minus of x1. x1 is nothing but, just now we have calculated here, 4 divided by 7 of xu, that is xu minus of 4 by 7 of xu. So if you simplify, you will get it as 3 by 7 of xu. So this distance will be, x2 distance will be 3 by 7 of xu, x1 will be 4 divided by 7 of xu. Then next is we'll try to calculate what is the total compressive force which is going to act and what is the total tensile force which is going to act. If you want to calculate the total compressive force, so this is at the top we have rectangular portion, at the bottom we have this parabolic portion. So what we'll do is we'll try to divide this parabolic portion, we'll calculate separately. For rectangular we'll calculate separately. We'll combine it at the end so as to get the total compressive force, and next we'll try to calculate at what distance it is going to act from the top. So first what we'll do, we'll try to calculate the force of compression in the parabolic stress block, that means this portion, bottom portion, parabolic stress block we'll try to calculate. How to calculate? I will consider this as C1. So this will consider it as C1, this I will consider it as C2. So how to calculate now? Area of this portion multiplied by width B. So how to calculate? It is 2/3 of base into this height. So 2/3 of base is nothing but this value. So this is nothing but, already we know, that is 0.446 FCK. Then next is this height. This height is nothing but x1. So that is x1. 2/3 of area of this parabolic portion we have multiplied by B. If you further simplify, that is instead of this x1, just now we have calculated value of x1, that was nothing but 4 divided by 7 of xu. If you substitute xu as x1 as 4 by 7 of xu, remaining is same, 0.446 FCK into B. Further if you simplify, 2/3 multiplied by 4 by 7 multiplied by this 4.446, you will get answer as 0.17. Remaining is FCK B into XU. FCK B into XU. FCK B into XU. This is nothing but total compressive force due to this parabolic portion. Next we will go to the rectangular portion. Now we will take this rectangular portion and we will mark this as C2. So how to calculate total force? That is area of the rectangular portion multiplied by width B. So area of the rectangle we have to calculate. This area of the rectangle will be, this distance is x2. x2 we have multiplied by width, that is 0.446 FCK. 0.446 FCK. Next is this width we have, area multiplied by width. So x2 value already just now we have calculated, that is 3 by 7 of xu we have. Same thing, remaining is 0.446 FCK B we have. So further if you simplify this, 3 by 7 multiplied by 0.446, you will get it as 0.19. Remaining is FCK B XU, FCK B into XU. So total compressive force due to this rectangular block will be 0.19 FCK into B into XU. If I want to get the total compressive force, what I have to do? I have to add this C1 as well as C2. Therefore, total compressive force, that is C, that is equal to C1 plus C2. C1 it is 0.17 FCK B XU. C2 is 0.19 FCK B into XU. So if we add up, we will get answer as 0.36 FCK into B into XU. This is nothing but the total compressive force which is going to act. So same thing already it is being given in the code book. So directly they have given this area of what you can say, area of the stress block, it is 0.36 FCK into XU. Next comes is we have to calculate now this C we have shown, this is nothing but total compressive force. Now at what distance it is acting, so that has to be shown. So at what distance it is acting from this top compression fiber, what is this distance, that has to be shown. So we will try to calculate this value K. So how do we calculate now? These are two forces which are acting. I have combined this and I have calculated one force, that is C. At what distance it is acting, that has to be calculated. So we will try to calculate centroid of that. So how do we calculate? A1 x1 plus A2 x2 divided by A1 plus A2, right? Therefore, first let us see what is this is a rectangular portion. So centroid of this, that is x2 bar, this is x2, as it is a rectangular portion. So x2 is nothing but what? 3 by 7 of xu, 3 by 7 of xu multiplied by 1 by 2. So therefore if you simplify, you will get answer as 3 by 14 of xu. Then next is x1 bar. So centroid of this, from this face, what will be the distance? So this will be centroid of this parabolic portion, it is 3 divided by 8 of x1. From here till here, this distance, from this face till this face, this is 3 by 8 of x1 plus this remaining distance is x2. Remaining distance is x2. We require distance from this face till this face. So this is 3 by 8 of x1, this is x2. 3 by 8 of x1 plus x2. So 3 by 8 of x1 is nothing but, already we have calculated 4 divided by 7 of xu plus xu, already we have calculated 4 divided by 7 of xu plus xu is nothing but, already we know that is 3 by 7 of x2 is nothing but 3 by 7 of x2. Further if you simplify, that is 3 by 14 plus 3 by 7 of xu. So if you simplify, x1 bar will be equal to 9 by 14 of xu. That means this x1 bar means nothing but this distance from this face till this face. This distance is nothing but x1 bar. From the top face, at what distance this force C1 is acting. So now in this formula we will try to substitute. Already we have calculated this forces C1, C2 we have calculated. Next is just now we have calculated this x1 and x2 bar. So if you substitute, we will get the value of K. That means at what, this is nothing but not x2, this is nothing but K. This is nothing but K. At what distance this is acting, that we have to calculate. C1 is nothing but, here if you see C1 is nothing but 0.17 FCK into B into XU. X1 bar is nothing but 9 divided by 14 of XU plus C2 is 0.19 FCK into B into XU. X2 bar, that is nothing but this value 3 by 14 of x2 divided by 0.17 FCK BXU, 0.17 FCK BXU. C2 is nothing but 0.19 FCK BXU. Further if we simplify this, we will get this FCK will be gone. Then next is this B we have, here we have B, here we have B. Then next is this XU we have, this XU will go, this XU will go. So remaining will be XU we have. Further if we simplify, this value of K will be 0.416 XU. So that is approximately it is 0.42 XU. That means if you take this figure, we are going to have a total compressive force C. It is going to act at a distance of 0.42 of XU. This is being given in the code book directly. This value it is being given. You can see depth of the center of the compressive force. It is going to act at a distance of 0.42 XU. So where XU is nothing but the depth of the neutral axis. Directly it is being given. So this is how it is being derived. So these are nothing but the stress block. These are nothing but the stress block parameters.